Hello everyone, welcome to the second lecture on this topic on velocity of separation. I am Dhiraj Madan. So this is a subtopic of kinematics as we had discussed earlier. Today we will be continuing with this topic and we'll be looking at a new problem again from the textbook by Irodov, and essentially this has some applications in warfare also. So let's see what is this particular problem. So before that, I'll just recapitulate what we did last time. So far what we have done is that we had find the concept of velocity of separation. So velocity of separation between 2 points A and B is essentially the derivative of the absolute value of the distance between the points, right? Absolute value of the position vector, which is the distance. So the derivative of the distance is the velocity of separation. So this is the definition. What we proved was that velocity of separation also equals the relative velocity, the component of the relative velocity along the line joining the 2 points. So that is what something we have seen. Okay, so we had proved this thing and we use this to solve a particular problem. Before that, I'll also want to make a remark that, let's say if instead of velocity of separation, you also want to generalize this idea to acceleration of separation, right? So let's say you want to compute d2 by dt square of s, right? So what is the second derivative of distance? So can we use the same thing? Can we still say that this equals acceleration of b with respect to a dotted with eba hat? So what do you think? So I would like you to pause the video for a minute and think about it. So actually it turns out that this relation does not hold true in general. And only in the velocity it looks that simple. So in acceleration it's not that simple as well. But again, we'll solve another problem based on the concept of velocity of separation. So this problem is also from Irodov. So this is the problem which actually shows some applications in warfare. Okay, so this is adapted from Irodov and it's adapted from problem 1.13 from Irodov. So that's not stated in these words, so it's slightly different. But we will look at the adaptation which we have created. So let's say we have an aircraft. So an aircraft A moves with velocity v or let's say velocity u along a straight line. Okay. And another drone, okay, B starts tracking the aircraft. Okay. And so it starts aiming or starts tracking the aircraft A. Okay. So how does it track? It moving along the line joining B to A. Okay, so whatever is the line joining the drone to the aircraft, it just aims towards that. It's aiming towards the aircraft and it moves along that direction always. Okay, so this direction will keep changing as before in the previous problem, but it moves with a constant magnitude velocity. With constant magnitude of velocity v. Okay, so initially the distance AB, right? So this distance equals L. And initially the line joining B to A is perpendicular to U. Okay, so basically this aircraft is moving with velocity U and line joining joining B to A is perpendicular to U. Next, you need to find or compute the time taken by the drone to hit the aircraft. So let's look at the question again. So basically the aircraft is moving with velocity u. Okay, so let's draw this. So we have this aircraft which moves with velocity u. Okay, so this aircraft is A. Okay. And we have this drone which is tracking this aircraft, which is aiming towards this aircraft, which initially begins with velocity v towards this, and this velocity, the magnitude remains the same, but it always aims towards A. So A is always moving with constant velocity, but B, once it moves a little, then essentially the aircraft would also have moved a little A, and essentially it will change its direction. And as it moves further, it again changes its direction, and so on. So essentially, we'll see that this drone will actually follow some curved trajectory and it is going to hit the aircraft at some point. So this aircraft is always moving with the constant velocity in the same direction, but the drone which is tracking it always keeps changing the direction and it curves so as to be able to meet it, right? So basically, whenever the direction changes, it also changes its direction. So basically, the direction always aim towards A. That's the point. And once you have sort of reached it, then you stop. Okay. And here, of course, we'll need to assume that V is greater than U, otherwise we will not be able to catch this. So that is the assumption. Okay. So how do we now solve this? Okay. So basically now let's try to solve this problem. So essentially first let's see, what else can we do if we do not use this idea of velocity of approach. Okay, how much is it that we can solve? So we have this aircraft A. Okay, so this is moving with velocity u. Okay, and we have this sort of this drone B. Okay, and initially, this drone starts with some velocity, but it always tracks the aircraft at whatever point aircraft is. It's always aimed towards the aircraft. So let us say, at any given point. So let's say let phi be the angle made by B with the x-axis. So let's say that so this is the velocity u, this is the velocity v so this velocity v will change with time, and let's say at time t it makes an angle phi t with the x-axis. Okay, and essentially this phi t will keep changing. So we need to find the time at which they are going to meet. Okay. So first thing to observe is that when they are going to meet, so we are not using the velocity of separation directly. We'll use it, when we'll need. So first see how much of it we can get without using that concept. So if we can parameterize this sort of this angle as phi t, then we can actually write down some equations already. So first we can say that the at point of meet. So this is how you solve the questions on collisions in general, right? Even projectile motions also, you might have seen some problems in collisions between projectiles and all. So you might want to adapt the similar idea. So let's try to do that. So at the point of meet, we know that the x components of aircraft and so there is an aircraft and basically the drone are the same. And how much is the x component of aircraft? So aircraft, the x component is just going to be integral of u dt. right? Because it's moving with constant velocity ui cap. So the x component is just integral of ut essentially. So capital T is the time to meet, I'm assuming. And this must equal the x component of the drone. Now the x component of the velocity of this drone is v cos phi. Right? So this is going to be integral 0 to t v cos phi t dt. So this phi t is actually going to change with time. So this is the first equation. So basically ut equals v times integral of 0 to t cos phi as a function of t dt. So how do I now integrate this? This is my first equation. I'll number it here. Now I'm also going to equate the y components. Similarly, the y components are also the same. Okay. So how much are the y components? So the y component of this aircraft is nothing but L, right? So let me keep my origin over here at the initial point of the drone. So this y component is L and it always remains the same. And how much is the y component of my drone, right? So the y component velocity is v sine phi. So the y component of the position is integral 0 to t v sine phi t dt. So this is my second equation. Now, can I use equations 1 and 2 to solve for capital T? Maybe we can, but it's very difficult, right? Because this phi is a variable and we don't, it's not very clear, how do we now write down the equations for phi t? Okay. So it becomes a bit difficult to solve this pair of equations directly. But the interesting idea is that now we can use the concept of velocity of separation. So use the concept of velocity of separation. Okay. So if you use that, then essentially, what is the rate of change of distance between these 2 points? The rate of change of distance is essentially uh, the component of the relative velocity with towards the line joining the 2 points. Okay. So basically, we need to take the line joining the 2 points, and we need to take the component of the relative velocity along the line joining the 2 points. Okay, so that is it what we need to do. So essentially, so let's say that at any given point of time, there is a line joining the 2 points. Now, the velocity of B along the line joining the 2 points, right, towards EBA, right? So that velocity is nothing but, right? So basically that is essentially V along the line joining the 2 points. And essentially it is minus V EBA hat, right? In terms of BA hat, right? So it's essentially minus of EBA hat. So EBA hat is the line from A to B, and this is from B to A. So this is minus of V EBA hat. This is VB. And VA, if I have to take the component along the line joining the 2 points, so essentially since this is x-axis, so if I along the line joining the 2 points, the angle made with the x-axis is phi. So essentially, this is going to be u cos phi, right? So essentially, this is going to be the component along the line joining the 2 points is going to be u cos phi EBA hat, and then there is a u sine phi in the perpendicular component, right? So u sine phi EBA perpendicular hat. Okay. So essentially, if I now look at my the VBA hat dot EBA hat, or essentially, if I have this aircraft A, this drone B, so at any given point of time, right? So if this is my angle phi, So essentially along the line joining the 2 points, the component of this velocity of b is just v, but this is going to be u cos phi. And essentially this u cos phi is in the direction from b to a, and v is against the direction from b to a. So overall this vba dot eba hat is going to be minus of v plus u cos phi. Okay, so just convince yourself that this is true. Right. So this is essentially ds by dt. And what I can write, okay, so this is like a differential equation now. So ds is essentially minus v plus u cos phi dt. And now if I integrate both sides from 0 to capital T, ds equals integral 0 to capital T minus of v plus u cos phi dt, right? So essentially this integral of 0 to t ds is essentially now going to be, so at capital T the distance is 0 and initially the distance was L. So this is 0 minus L, which is minus L. And this is going to be 0 to t of minus v dt plus u times integral of 0 to t of cos phi dt. So what we get is that minus L is minus of vt plus u times integral of 0 to t cos phi dt. Right. So this is my equation number 3. So there is an integral of cos phi in equation 3. And there is an integral of cos phi in equation 1. So from 1 and 3, we can actually eliminate this integral of cos phi, and then we'll get a relationship which relates capital T, u, and v. So from 1, if I try to eliminate integral of cos phi, I get integral of cos phi is ut over v. Phi from 0 to t is cos phi dt is ut over v. So if I substitute this over here, so what I get is that minus L equals minus Vt plus U times Ut over V. Okay. So essentially, if I now so if I now just change the sign, so what I get is L is Vt minus of U square over Vt. Okay, or capital T times V square minus U square over V. So from this thing, if we solve, so we'll get T equals LV over V square minus U square. That is the final answer as well. So let's just recapitulate what we did over here. So this problem was that essentially there is an aircraft which is moving along the straight line, let's say the horizontal line U, and a drone which is not tracking this aircraft. So as this aircraft moves, the drone will keep on changing its direction. And ultimately at some point they are going to meet each other. So let phi be the angle which this particular drone makes with the x-axis. And now we can write down the two equations which ensure that their x components and y components at the point of meet are equal. Now we found that maybe we can solve, but it appears that it's a bit complicated to solve those particular system of equations. So we wanted to go back to the idea of velocity of separation. So velocity of separation is essentially the rate of change of distance. We have seen that this equals the component of relative velocity along the line joining the 2 points. So if I have to take the component of relative velocity along the line joining the 2 points, I can just take the difference of the components along the line joining the 2 points. So we have this v, right? So which is moving already along the line joining the 2 points. So the component is essentially minus v over here. It's essentially the magnitude is still v of that component. Essentially, but from A to B, right? It's in the direction from B to A, and EBA hat is in the direction from A to B. So there is a minus sign of minus V. Now for A, which moves along the x-axis, right? So since x-axis makes an angle of phi with the line joining the 2 points. So if I take the component along the line joining the 2 points, I'll get u cos phi. and this is in the direction from B to A already. So since it's in the direction from this B to A, so there is no sort of minus sign over here. And what I get is that ds by dt is minus v plus u cos phi. Right. So this is the rate of change of separation. And yeah, so actually this is okay. So both of these components are in the opposite side. So basically we'll need to look at the direction of EBA hat, which is essentially the direction from A to B. And both of these are from B to A, but essentially if I do VB minus VA dot EB hat, so basically VB dot EBA hat is minus V, and VA dot EBA hat is minus U cos phi. So minus of minus U cos phi gave us plus cos phi, U cos phi, and overall we got this as minus V plus U cos phi. So essentially you need to first compute VBA, and then you need to look at its component along the line joining A to B. So the relative position of B with respect to A. So you take the unit vector along that, which is the line joining A to B, and then you take the EBA hat. That's how you'll get it. And when we computed the differential equation, essentially we again got an integral of cos phi, which was there in equation 1. So, if you compute this integral of cos phi from equation 1 in terms of Vt and U, substitute over here in equation 3, you can then solve for capital T, which gives you this final solution. But that is what we have done over here. So I would want you to go back and try to do these calculations yourself and convince yourself that you can understand and solve this problem. So this is actually a tricky problem, and it might be difficult to solve this for the first time if you see it in an exam. But this is something which helps in enhancing the concepts of this velocity of separation and also shows their applications. So thanks a lot. Bye, and see you sometimes in future again.